Let's give you another example which may make you understand more. So in this particular case, we want to maximize x1 subject to 3 less than or equal to constraints with 2 non-negative variables. So we get to the standard form by adding 3 slack variables. And then we prepare our initial tableau. Pretty much for constraints, we simply record everything. We just copy and paste all the numbers. For the zeros row, I hope you still understand why we want to have a negative multiplication there. We were going to multiply each value by -1 because that's the way for us to get the equation with respect to z. So once we have that, we know this is a set of basic variables. That's for x3, x4, and x5. We get this because there's an identity matrix here with all zeros there. So we get this for free. And then for the other x1 and x2, that's non-basic. Okay? For this maximization problem, we look for negative numbers in the zeros row. Because we do this for so often, those negative numbers, positive numbers in the zeros row are so important. Starting from now, we will give them a special name. They will be called the reduced cost. The numbers in the zeros row are called reduced cost. Why is that? Well, the name somehow means if you consider this as a minimization problem, okay? I want to minimize the total cost for us to produce something. In that case, your C transpose X, those C are cost per unit, something like that. Okay? So you are looking for a way to increase the production of some variables so that you may decrease the total cost. And if you want to do that, you look for positive numbers in the zeros row. And those positive numbers tells you if you increase this variable by 1 unit, how much of the cost would you decrease, would you reduce? That's why these values are called reduced cost in general. Okay, so we look for negative reduced cost for maximization problems. We can see that, so this one should be an entering column, entering variable. We're going to choose x1 to enter. And then we want to divide the right-hand side column by the entering column. We want to use 4 to be divided by 2, 8 to be divided by 2, and 3 to be divided by 0. And here, we are going to ignore this particular division. We're going to select enter a living variable by considering just x3 and x4. Why is that? Because if you think about the fact of entering x1, when x1 goes up, if this number is 0, what does that mean? That means it has no impact on x5. Okay? When x1 goes up, your x5 would still remain to be 3 forever. That means your x5 has no way to hit 0. So x5 or constraint 3 does not create any problem from you. Or you may say constraint 3 is not in front of you if you move along increasing x1. Okay? So this 0 happening in the denominator tells us that increasing x1 does not affect x5. So we only focus on the first 2 rows and pick the one with the smaller index. We will call this as the ratio test. So x1 should enter, x3 should leave, and then we say we pivot at 2, or we do the next tableau by pivoting at 2. We consider this number 2 as our pivot. So we multiply the first constraint by 1/2, and then do some elementary row operations to get this 0, get this 0. That allows us to get our next tableau. For the next tableau, we have the identity matrix here and there for variables x1, x4, and x5. Now we have the new basic solution, basic feasible solution, which is 2, 4, 3 for x1, x4, and x5. And for the others, that's 0. We want to know whether we should continue. Okay, so we look at the zeros row again. We identify a negative reduced cost. Then for this maximization problem, that should be an entering variable. So your x2 would enter. Now you apply ratio test again. Well, you may see that now we have a negative number at the denominator. What does that mean? That means if you increase x2, that's going to make your x1 even larger, all right? So that means constraint 1 has no way to prevent you from keep improving your x2. Constraint 1 is again not in front of you, all right? So if that's the case, you may eliminate constraint 1 from the selection of a living variable. You only consider 4 divided by 2 and 3 divided by 1. And very quickly, you would see that row 2 wins the ratio test with a smaller ratio. So x2 should enter, x4 should leave. We have a pivot, which is this number 2, and then we pivoting. So once we do it again, we may see that we get a third basic feasible solution, which is 3, 2, 0, 0, 1. It is optimal. Why? Because all the reduced costs are now non-negative. So there's no way for us to improve this solution, and then we report this as an optimal solution. So typically in this case, we would write x star as our optimal solution, and that corresponding optimal objective z value is called z star. So our z star in this case would be 3. Graphically, you may verify the correspondence again. So we have two initial original variables, x1 and x2. So every time when you get a basic feasible solution, if you focus on x1 and x2, focus on the two variables, okay, then we would see that they indeed corresponds to some extreme points at the feasible region for the original feasible region. Also, when we see that we do one iteration, next iteration, we always move along edges. It should be quite clear. We always do iterations when we find an improving direction. And once we move along that improving direction, there are some constraints in front of us. And the ratio test will tell us when to stop. That's how we get the improvement. And that's how we do iterations. The simplex method do all the things in algebra. That's how a computer program may be correctly constructed to execute the simplex method. But still, we know it has some correspondence with the geometric ideas. Okay, so I hope we may appreciate how the simplex method is decided or is defined so that it somewhat simulates the geometric search, but in an algebraic way. That somehow make the computer search feasible.